Okay, so Professor Hell started his career in 1991 in Heidelberg, where he worked on 4-pi microscopy. Then in 1993, he became a group leader at the University of Turku in Finland. And already then, he started to develop his now famous method of stimulated emission depletion microscopy, or STED. Then in 1997, he joined the Max Planck Institute in Göttingen for biophysical chemistry, and he got appointed director there in 2002. And if I'm not wrong, in 2003, he started a second research group in optics in Heidelberg University. And of course, very notably, Professor Hell was awarded the Nobel Prize in chemistry in 2014 for the development of super resolved fluorescence microscopy. And so, of course, it's a huge honor to have Professor Hell with us today. And thank you so much for accepting our invitation. And I'll just say before giving the floor to you that we please ask to ask questions. At the end, there will be ample time to ask Professor Hell any questions. So please do not interrupt him during his talk. Professor Hell, the floor is all yours.
Thank you very much, Serge, and thank you very much for giving the opportunity to speak actually here at this Israel Physics Colloquium. It's a great pleasure. I remember my visits in Israel, and they've been always very, very fruitful, and I had many, many collaborations with and the discussions with physicists in Israel. To come to the topic itself, so I'm going to speak about how the resolution of fluorescence light microscopy fundamentally changed during the last 20 years. Now, in the 20th century, as you certainly will recall, or many of you will recall, the resolution of any light microscope, especially also of fluorescence microscopy, was fundamentally limited to about half the wavelengths of light, which amounts to about 200 nanometers in the focal plane. And the gold standard of, say, of any light focusing fluorescence microscope was confocal microscopy. But again, the confocal microscope didn't achieve a higher spatial resolution than 200 nanometers. It mainly added the third dimension of resolution in the Z direction. This was changed by the development of STED microscopy. And STED microscopy, I think one of its merits is that it showed that there is physics, actually viable physics, that allows you to overcome the diffraction resolution barrier and come up with pictures that have a spatial resolution that is better, roughly up to a factor of 10. So the resolution was improved in a number of cases down to about 20 nanometers. Now, as Serge just mentioned, this has led to a share of the Nobel Prize in Chemistry 2014. And the reason why I'm showing you this poster by the Nobel Foundation is not because I would like to brag with the Nobel Prize, but because it very nicely shows the situation at the time the prize was given. And if you look here at the poster, you will see a sketch of STED microscopy. And STED microscopy has as a basic feature a beam that turns molecules on, fluorescent molecules on, in order to cause them to emit fluorescent light. And a second beam that is donut shaped that causes the molecules not to emit spontaneously. So that stops the fluorescence. And then, of course, the region in which fluorescence is allowed is confined in space, simply because the stopping beam, the stimulating beam, is shaped as a donut. So there is a second method that also shared the prize called Palm Storm. It has the same, the very gist of it. It has the same principle. It's also about turning molecules on and off, but the major difference here is that molecules are turned on and off individually, stochastically individually. Now, as I said, these two concepts have the fundamental principle for separation of molecules in common. And another thing that they have in common is that they can, in principle, achieve a spatial resolution that is at the size of a molecule. So both STED microscopy and also Palm Storm, which was initially demonstrated by Eric Betzig, in principle, they can achieve a spatial resolution that is of the order of a nanometer. But in practice, if I may say so, they don't. Usually, both methods do not provide a spatial resolution that is better than 20 nanometers. And so the Nobel Foundation put it actually quite right at the time the prize was given. These microscopes, STAT and Palm Storm, which shared the prize, crossed the threshold of the diffraction barrier that was, say, coined in the late 19th century, but did not attain the ultimate limit. So that's what I added. So the ultimate limit was not attained. And I got fascinated with this resolution problem many, many years back, as Serge mentioned, in the late 80s, early 90s. And after the prize, my goal was to attain just that, attain a spatial resolution that is truly at the molecular scale. So the size of a molecule, and the molecule is typically about 1 to 2 nanometers in 3 dimensions. So my group and I actually focused on this problem. So we wanted to come up with a fluorescence microscopy that really gets down to the absolute limit, conceptual limit of any fluorescent microscope, which is, of course, a resolution that is at the size of the molecule itself. Now, in order to explain to you how we got there, and we are now at that level, I would like to walk you through a bit through the basic concepts of overcoming the diffraction barrier. And as a physicist, of course, you will ask, so why can we now attain a spatial resolution that is much, much better than the diffraction barrier? There must have been, say, a fundamental, say, physical ingredient that has made this transition. And I'm going to explain this to you now. Now, what was the problem? The problem was the following. So if this is the sample consisting of molecules, and this is the lens, of course, if we could focus the light onto a point, as we all know, on a single point, we could address molecules individually. And then we would have, of course, in principle, and also in practice, a spatial resolution that is at the size of a molecule. But we know that this is not possible because of diffraction. We cannot address molecules individually by focused light. We would rather get a blob of light that is limited by diffraction. So it has a diameter of about 200 nanometers in the focal plane and 600-700 nanometers along the optic axis. And as a result, we will address many molecules at the same time if there are many, say, in close proximity. And this is why we cannot, say, separate the molecules individually, because we cannot address them individually. Now, the same problem exists actually in reverse. If we image the fluorescence or the backscattering of molecules into the image plane, then of course each of the molecules will produce a diffraction blob of fluorescence light at the image plane, at the detector, no matter what the detector is. Could be the eye, could be a photomultiplier, could be a camera. And you can imagine that each molecule will produce a blob of diffracted fluorescence light here at the detector, and the detector will not be able to tell the signal apart. Now, the solution to this problem was, and this is the only fundamental solution to this problem. So this basic element. So as a physicist, of course, you always want to know, what is the essence of something? What is the element that you could not reduce, because if you reduced it, it wouldn't work? Is this. The separation is done by an on-off transition, meaning that you make sure that not all the molecules that are here covered by the excitation light are in principle, say, addressed by the excitation light, are in the end capable of scattering fluorescent light back. So these molecules here that are shown here in black are turned off. So they have to undergo a state transition into a state in which they are not capable of sending light back. And if you manage to do so, then it's very obvious that this confusion here at the detector is not there anymore, because there's only one molecule, or maybe a bunch of it at close proximity, for that matter, that is capable of producing light at the detector. So the element that really broke the diffraction barrier, the fundamental element, was the insight that you do the separation not by the focusing of light, as people have thought, not by making the light waves sharper, that doesn't work, but by making a state transition that tells molecules apart by their state, namely, say, backscattering or not backscattering. Okay, now, if you realize that the most obvious way of turning fluorescent molecules off, especially if you're trained as a physicist, is the first thing that comes into your mind, is to do a state transition that pushes the molecule from the backscattering fluorescent state to the ground state, and that's stimulated emission, obviously. You just push it back down, and then fluorescence doesn't happen. And this is why STAT I think was historically the first concept that worked according to this principle, because this is the most obvious thing that you would do when you want to turn molecules off. I mean, stimulated emission just kicks them down to the ground state, and spontaneous emission is not possible anymore because the molecule is already pushed back down to the ground state. So in other words, this transition doesn't allow the occupation of the on state, because as soon as the molecule gets up, it's instantly pushed back down. Okay, so a hallmark of this STAT microscope is that the position of the emissive molecule, or the position where the molecule is still allowed to emit light, is clearly determined. Why? Because for stimulated emission, we use a beam of light that is shaped like a donut that has a hole in the center. And here in the center of the hole, there is no, say, off-switching light. There is no stimulating light. And therefore, only those molecules are allowed to emit. And so it's always clear where this on state is occupied, where in space. So the position in space is very clear. So we inject, so to speak, the position of the emissive molecule into space by injecting a pattern of light into space that is shaped as a donut. Okay, now Palm Storm doesn't do that. Again, on-off is the way to separate molecules. As I said, this is the fundamental ingredient for all these concepts. But here the on-off transition is done in a purely stochastical way that works for some molecules that undergo, say, conformational changes or so. You turn on just one molecule that is capable of scattering light back, and then you separate this molecule from the rest, because only this one is scattering and the rest is not scattering. So those are off, although they are, say, flooded by the excitation light, by the diffraction limited excitation light. But here the separation is, as I said, due to the fact that you have an on-off state transition. But since this is turned on stochastically in space, one has to find out where the molecule is located. And this is done by a pixelator detector, a camera, and the positions of the pixels here basically determine the position of the molecule in space, or they allow one to determine the position of the molecules in space. Because if the molecule emits many, many photons in a bunch, which it usually does, if it's a, say, conformational switch, then you get a pattern of fluorescent light here at the detector. And then you can say, okay, if this is a whole pattern and say 100 or 1,000 photons even coming from the same molecule, then it's not a big deal to find out where the molecule is located, because you just calculate the centroid of this pattern, and then you know where the molecule is, because this center of the pattern must relate in space with the position of the molecule by simple geometrical optics. Now, the precision, of course, with which you can determine the center scales inversely with the number of photons that are collected here by the camera. The more photons you have, the more precise, of course, this position will be. If you have, say, 10,000 photons in principle, you get a precision that is 100 times better than the diffraction barrier, at least in the simplistic case in theory. In practice, you don't, but at least in the simplistic case. So this is the difference actually between the two methods, STAT and resolve. They share a common basis for, or a common principle of separation, that is this on-off transition. So yellow means backscattering, black not backscattering. But the way the coordinate is made, and that's my point now, the way the coordinate is determined is fundamentally different. So here instead, the coordinate of emission, the coordinate where the molecule is determined by the light that comes from the laser, because it's the stimulated photons. So the red beam, that is the beam that determines where the molecules are on. And here, of course, it is the photons that come from the dye, the fluorescent photons, that determine where the molecule is located. You always need many photons to determine the position. It's very clear, because one photon simply goes somewhere within the diffraction region, okay? But if you have many, you can produce a pattern, and then you can calculate, so to speak, the statistical average, and then you can determine, so to speak, a coordinate. So in order to make a coordinate with photons, of course, you always need many photons, very obvious. But here, as I said, you have the photons from the laser, which is very good, because there's no shortage of photons from the laser. So the precision with which you can make this coordinate is very, very high, because it's done with the zillions of photons that come from the laser. Whereas here, there is a problem, because Here the photons come from the dye, from the fluorophore, from the backscattering molecule. And then, of course, this can bleach, this can stop scattering and so on, and there is a problem. And you see the weaknesses and the strengths of the two methods. So the weakness here is that the coordinate determination is done with the photons from the dye, but the strengths here, in the case of Palm Storm, is that the separation is single molecule based. So that is the best possible separation you can imagine, because it's, even if two molecules are close, they can be separated. So this is the best separation. Whereas here, as I said, there could also be two molecules very close together if you don't do a stochastic separation, and that's the weakness here. So my reasoning was, why not combine the two strengths of the methods? Namely, take the many photons from the laser to find out the position, but do the separation actually in the stochastic way, molecule by molecule, because if you combine these two strengths, then you can come up with a concept that is better than any of the two, better than STAT and better than Palm Storm. And this is the idea behind this min-flux concept, about which I'll be talking in the next 30 minutes or so. Now, just to be clear, so it's, in essence, it's about the new way of determining the position of a molecule with very, very high precision, given that you have a single molecule, okay? So if you have many, of course, you have to turn just one on in order to have just one molecule. So let's assume we have turned on one molecule, like this molecule, and then we want to find out where it is in the most, say, effective way. Now, usually what people did in the past, and they're still doing it, they have a kind of wide field illumination, so the whole focal plane is illuminated with green light, so this is why this is shown in green. And then the fluorescence that is produced by the single molecule is collected by the objective lens and is projected onto a camera. And the camera consists of many pixels, as I said, and then you get this diffraction spot actually on a monitor, because the monitor just shows what's on the camera. And then, as I said, you calculate the position of the molecule just by calculating the centroid of this pattern. And the more photons you have, the better the precision will be. That's why it's called localization. Okay, but we are not going to do it like this, because, as I said, if you do it like this, you need to maximize the number of photon detections, fluorescent photon detection, and that is not always possible, because the number n of photons is limited by bleaching. If you have to wait for large n, it's getting slow. And then there is another, say, serious physical problem. As you will appreciate, we have, of course, in these molecules transition dipole moments. And then what happens actually is if the molecule is oriented like that, if the transition dipole is oriented like that and not like this, and slightly off the plane, then the pattern shifts in the image plane. And so there is also a problem with the fact that, of course, in essence, these are dipole emitters, of course, any fluorescent molecule. Now, and the basic idea behind what I'm going to show you now is the following. Since the number of photons, fluorescent photons, is limited, why not localize with the zillions of photons that come from the laser, as it is done in STAT microscopy? I'm going to show you now how this works. Now, again, green means light for exciting fluorescence, and yellow means light that is fluorescent, that is detected light. Now, we localize the molecule not by using a camera. So in this case, it's just a normal detector with a pinhole. So it's like a normal, if you will, scanning confocal microscope. And again, we do not illuminate in a plane manner, like illuminating the whole focal plane, but we produce a donut here in a sample space. Okay, this is why we have this profile, okay, this donut-shaped profile. And the good thing about the donut is that it injects a coordinate in sample space. So if you have this donut, then of course the center of the donut, where the intensity is 0, is very precisely defined. And not only that, is precisely defined, but it can also be perfectly controlled by any beam deflecting device. So you can have a mirror here that shifts the donut around in sample space, and you will always know where the 0 is located. And now if this is the molecule, then you can say, okay, I can find out where the molecule is located with respect to the zero of the donut, because the brightness of the emission of fluorescence must depend on the distance. The closer the molecule is to the zero, the less fluorescence will be detected at the donut, because if the two coincide in space, there is no fluorescence, because the excitation light basically is absent here. There's an intensity 0 here at the donut, at the center of the donut, and this is why there is no fluorescence. And if it's slightly off, of course, then fluorescence will increase. So in other words, the brightness of fluorescence emission will tell us how far the molecule is away from the center of the donut. And this is a very useful feature, because then we can kind of quickly and very effectively determine where the molecule is located just by measuring the distance to the zero. And that can be found out by looking at the absolute brightness. And I'm explaining to you in a second why this is so effective in terms of the number of photon detections that you need in here, why this saves photon emissions, why this is so effective. And in order to explain this to you, I've come up with a little thought experiment, Gedanken experiment. And this is a demon. And this little demon can act on the beam deflector. So in essence, the demon can shift this donut around in sample space. And let's assume for the moment the molecule starts moving. What will happen? The demon, because the demon is very clever, it knows exactly where the molecule is going. And this is why it shifts the detector around such that the zero of the excitation donut always coincides in space with the fluorescent molecule. And what will happen in this case, there will be no emission, zero fluorescence emission. Yet the demon can trace perfectly well the position of the molecule, because the position of the molecule perfectly coincides with the position of the donut. So in other words, you can construct, well, not in reality, but in this thought experiment, a way of localizing the molecule without requiring any single fluorescence emission. So the absence of fluorescence emission actually is a way to detect the position of the molecule. And this is totally opposite from what you've known or what people have thought that is required. Namely, it takes many fluorescence emissions in order to find out where the molecule is. This is just the opposite of it. In essence, in this limiting case, you don't require any fluorescence emission in order to find out where the molecule is. And so this thought experiment tells us that you can have in theory, of course, or in this limiting conceptual case, a precise localization without any fluorescence emission. And then there's another startling thing that becomes obvious in this case, and the precision of localization will not depend on the wavelengths. I will come back to that in a moment, because this is really an interesting insight. There's no wavelength dependence on the precision of localization. So in the previous case, of course, it always scales with the wavelengths, or also instead, if you localize with that, scales with the wavelengths. But here you will see that there is, in first approximation, no wavelength dependence whatsoever. Now, demons do not exist, as we all know, but we can kind of approach the situation by making an electronics, a controller that detects a number of fluorescence emissions, a number of fluorescent photons, and then acts on the beam deflector. And then if the molecule, as I said, moves, then of course, and if the zero of the donut, of the excitation donut, does not coincide with the molecule, there will be some detections in here. But from the number of fluorescent photons that are emitted per second, so to speak, from the rate, we can infer actually on the position of the molecule. And then we can position the donut such that the zero is shifted towards the position of the molecule. So you can kind of approach the demon situation by measuring the fluorescence here, and then push the donut such that the two hopefully coincide in space. Why is this thought experiment so important? Because it shows that in this case, you can save fluorescence emissions. Why? Because the majority of the localization of the molecule is done by the photons that come from the laser, by the green photons, by the excitation donut. And only the rest between the zero and the molecule, so the few photon emissions, only those are used just as for a refinement. So they are just indicating how far we are from the zero to the actual position of the molecules. But of those, you don't need many in order to find out where it is, because the distance is so small. And this is a big advantage over the normal way of localizing molecules, where you look at the diffraction pattern and calculate the position of the centroid. And I'm show you why this is so effective. Now let's assume this is a molecule here again, and then we don't know where it is. So it could be anywhere between those 2 points, this point and that point. And then it could be here, 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 but let's assume for the moment it is here. And we have this donut. And how would we find out where it actually is? So we would move this donut across the molecule from here to here. And then at a position where the zero of the donut coincides with the position of the molecule, fluorescence will be zero. Now this is here the profile of the donut. This is the profile of the donut, the intensity profile. And this is the molecule again. And now if the donut moves, now it coincides with the molecule. Fluorescence is of course zero. Okay, now it coincides. Okay, and this fluorescence is zero, and we know where it is, where the molecule is. It must be where fluorescence is zero. Okay, now this doesn't mean actually that we have to move the molecule. We don't have to move the donut precisely across the molecule like that. This is not a fundamental requirement, because if you know that this profile here is a certain function, say in the first approximation is a quadratic function, it's perfectly enough to measure the fluorescence at the two endpoints. And if this is a quadratic function, we can calculate where the zero will be. So in other words, we can have the donut here and then jump right away to here, measure the fluorescence at the endpoints, and then we know that the molecule is there. We don't have to go slowly over the molecule, because this is just a quadratic parabola. And because it's a parabola, it's clear where the zero of this parabola is if we just measure the 2 points here. And this is very useful, because if you do this simple solution, find a solution of this simple quadratic equation, which is 7th grade algebra, then you find xm is given by this distance L, where we assume the molecule to be located, divided by unity plus the square root of the ratio of the fluorescence of the two endpoints. And then if you look at this equation, it's very simple, very simplistic, as a matter of fact, but it shows you two things. There's no wavelength dependence anymore. It doesn't depend on the wavelengths. And there is no molecular orientation dependence. And this is really a big improvement over the normal way of localizing individual molecules. And if you look now at the precision that you can get, the precision sigma, you will find that it scales with the distance L. This is the uncertainty that we start out with, divided by the square root of the number of photons that are collected in total. So that's N0 plus N1. So this is why we have this number of photons. And this is very interesting. Why? Because it shows that it's not worthwhile waiting to collect more photons to be more precise, as is usually done. It's better to reduce this distance L. So once you have a rough estimate where the molecule is, so if you know, if you measured the position of it and you know roughly, oh, it's somewhere in here, it's better to reduce this distance L and make the measurement again, okay? Rather than wait for more photons, because if you wait for more photons, it will scale only with the square root of the number of photons. But L, of course, has a linear dependence. So if you cut down L by half, then you will improve the precision by half. But if you double the number of photons, it will be only a square root of 2. So in other words, it's always better to bring the zero closer to the molecule than to wait for more photons. And this is not surprising if you think about the Demon experiment. ideally you want to put the 0 on top or just to the molecule, because then you need the fewest, the smallest number of photons in order to locate the molecule. So this is the basic insight. Just try to match the 0 with the position of the molecule, then you don't need many photons, because the distance between the two is basically 0. Okay, now in 2 dimensions, it's not a simple algebraic function. It's a bit more complicated, but not really complicated. So in essence, 3 points are enough. You measure the fluorescence by placing the donut to 3 different points. Having a 4th point has advantages. So we've done the experiment actually with 4 points. And then you measure what you get, and then you can calculate actually where the molecule is located. So you make a kind of triangulation. You go here, 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 and here. Then you know where the molecule is located. So the equation is a bit more complicated, but in essence, the physics is the same. The precision scales, of course, linearly with this region L, this diameter L, where the molecule is supposed to be located. Now, usually it starts out with the diffraction limit. So in the first place, if you start out, the diffraction limit is 200 nanometers, so L would be 200 nanometers, but then you could scale down to 100 or to 50 or 20, and then you're getting more and more effective. Again, scaling down L is better than waiting for more photons. And here there is experimental proof that the number of fluorescence photons that you get in order to find out the position of the molecule is reduced in this method. Here with 10, and literally 10 fluorescent photons, you get a precision of 10 nanometers in sigma, whereas with a camera, the normal way of localizing molecules, you would need 290 photons, so 29 times more photons, meaning you would have to wait 29 times longer to get the same precision, or your dye must not bleach before that, and so on. And this is a substantial advancement in the field, because it shows you that say zooming in on a molecule with a 0 is a substantial progress over just waiting for more photons. Now, you can use this for imaging. For imaging, you have to turn molecules on and off individually for separation, as I explained, because this is the key to separating and to overcoming the diffraction barrier. That's one option. But of course, you can also use it for molecular tracking. Many biophysicists are interested in, say finding the trajectory of a molecule, and they want to find that molecular trajectory with very, very high precision. And then, of course, this method is also more effective than just imaging something on a camera. So I'm just saying that. And an example of the latter is where we just follow the trajectory of a molecule is shown in here. So this is a ribosomal subunit that kind of meandered here in a bacterium, and we've managed to follow this trajectory of this protein actually with very high precision. So 8,000 localizations per second, which is very fast, and is a sort of record actually in following molecular trajectories. Why? Because we need much fewer photons in order to get the same level of precision. But I'm an imaging person, as you will know. And as I said, at the time the Nobel Prize was given, molecules that were that close, like 11 nanometers or so, could not be separated, neither with STAT nor with PALM. Didn't work. So here there would be a PALM example. But then with this min-flux concept, turn on molecules individually, like in PALM, of course, but locating it with a donut allowed us to separate the molecules, as you can see in here. Don't forget, on-off is the basic requirement for making a separation. In other words, each of the molecules was on at the time the rest was off. Otherwise, we would not have been able to separate it. But now you see it's clearly separated, and the molecules are really told apart. Even at 6 nanometer distance, not possible with Palm Storm. Here with this concept min-flux, it was possible. And since many of you or most of you are physicists, I mean, for me, it's still mind-boggling, I must say, and it's almost like a dream that has come true. 25 years back, I mean, if somebody said, okay, at some point we will be able to separate molecules at 6, 7, 8, 10 nanometer distance just with a regular objective lens, so not near field optics or so, just with propagating beams of visible light. I think everyone would have been said, this is crazy, this is never going to work, this is fundamentally not possible. But now it's reached. It's possible to have molecule size spatial resolution, say with far field optics, with freely propagating light. As I said, the separation done by on-off, and then here finding out a position with a donut that matches actually the position of the emitter. Now, at the time we published this, this was 3-4 years back in Science, people said, yeah, but you may not be able to do this on a large field of view. Of course, why not? Because that's just engineering technology. If you go over a large field of view, you will get large field of view pictures. And I'm not going to bore you with this, but for the sake of completeness, I'm going to show you that, of course, you can take large field images. These are so-called nuclear pore complexes. This is a protein complex in a cell. And now, if you go into the details, we have great confidence, and there is, the probability of the emission or the emission statistics speaks for the fact that these little dots that you see in here are attributed or can be attributed to individual molecules. So you're basically down at molecule size resolution here, although it's all done with focused visible light and with a regular objective lens. Now we compared with STAT, which, as I said, got the highest accolades. STAT is 10 times worse than this. And of course, confocal, which is the standard of the 20th century, is 100 times worse than this. So again, from here to here is a factor of 100. And this is showing actually that tremendous progress has happened. And one of the lessons to be learned is you should not underestimate the development of science, because it may take twists and turns that are totally unanticipated. And so I think that's a good thing about working in science. Sometimes things come up that you do not anticipate. And I think this is actually showing that we as scientists can do something that is really nice and not really anticipated. Can you do it in 3D? The answer is yes. It can be done in 3D. This is now, if you do it in 3D, then then you have to move a pattern also in 3D. And in this case, it's not just a simple donut like that. So it has also something above and below. And then you can move the pattern above and below, and you get a three-dimensional rendition of a three-dimensional object. And this is again a nuclear pore complex. And I'm highlighting the fact that this is a precision in Z of 1.6 nanometer, done with a single lens, by the way. This is, if you will, is a sort of world record again. In X and Y, it's 2.2. So it's not bad. And it shows that you can basically image three-dimensional protein complexes in a cell. Here, application in neurobiology, this is a certain protein called PSD95 in a synapse, again done with this type of pattern that gives you a three-dimensional, say, localization precision. Now, I'm acknowledging here the people I have contributed to this development. They have left my lab and they've done a great job. So Francisco has now an independent position in Vienna, and the three here, the others are working now. They work now for a big optics company. I would like to summarize at this point, say the parameters. The resolution can be, given that you say turn on and off molecules individually, can be of the order of 1 to 3 nanometers, so molecule size. And then movements, you can do a back of the envelope calculation. Within 10 microseconds, it's possible to get about 1 nanometer precision within a 10 nanometer range. We haven't demonstrated that yet, but this is possible. So there is, if you look into the statistics of photon emission, this must be possible. Applications like imaging, say, maps of proteins anywhere, the synapse, on vesicles, and nuclei. One can look at molecular dynamics. So I think there's a big area of application. The limits right now, if you ask me what are the limits, is the labeling. That's the limit. You need to label your proteins. We need to have fluorescence. We need to be able to turn molecules on and off. So this is the actual problem that is still left. It's not the physics anymore. I think the physics more or less is sorted out. It's the way you label the molecule, because the size of the label or the linker or so, that is now determining the usefulness of the technique. So what about STAT? I mean, STAT, as I mentioned, was the first method that really overcame the diffraction barrier. Is that now totally obsolete and useless? The answer is no, and this is basically the last part of my my presentation. Still, STAT has a number of advantages, and I'm just repeating what STAT actually does. You have an excitation beam, then you have the STAT beam for de-exciting, for turning fluorescence off, and then you have a region in which fluorescence is still allowed. So we usually call it the effective region of emission, okay, or EPSF. And now, what it means actually is that you have a region here where there is no fluorescence emission, and here you have a region of emission. There's nothing new, and the region of no emission coincides actually with the donut. So there's now a difference to the previous case. Here the donut turns fluorescence off rather than on, so it prevents the emission. Okay, and this has advantages. So you can imagine implementing now a concept like min flux, like the previous one. We've called it min stat, which is just to show the analogy, because now you can use this little thing, this little sharp region, as a way to create a kind of excitation donut. And in the following way, you just make it rotate. Okay, if this thing rotates, it mimics kind of a donut, and then you try to kind of bring it in the middle, bring the molecule in the middle. And then you can locate the molecule. So you kind of, it's a very similar concept, but the difference here is that you have the zero, so to speak, outside rather than inside, and you bring it inside by making it rotate, make this region rotate. And this has advantages because the background goes down. So this is so if you have something that turns off, then you turn off also background, spurious background in the sample. So it's a kind of technical advantage. There's no conceptual advantage, but a big technical advantage. And so if you sharpen up this donut, so to speak, by increasing the stat power and make this region smaller, then the precision, of course, increases substantially. For those of you who are kind of familiar with that, the fluorophore is never ever in the region where the stat beam is strong, so it doesn't bleach, and the inactive fluorophores are completely off, so there is no bleaching problem. This is also a very big advantage over the standard stat methodology, because you can apply relatively high peak intensities without having any issues. And this, of course, in conjunction with the fact that the stat beam keeps the background low, has allowed us to really make this method very effective. So you see, with 100 photons, we are down at a precision of 3 nanometers. Now, this is not bad. 100 emissions or detected emissions down to sigma of 3 nanometers, meaning that you can quickly actually measure the position of a molecule. Again, if you turn it on and off, you can make the separation. Then in conjunction with this way of localizing individual molecules, you can get a very high spatial resolution. And this is shown in here. Again, standard confocal, then standard stat, and now here this min stat thing, again down to a sigma of 2.1 nanometers. So it's basically the size of the molecule. And here in the sample where you have, of course, always have background, is about 1,200 counts. So that's not much, and still can be done better. And it shows that again we're down at a resolution that is basically at the size of the molecule itself, and although we use just focused visible light. A technical advantage is also that you can tune the resolution from the diffraction limit down to the molecular scale. And at the end, I would like to give you 2 insights. Apart from the statistical, say, conformational on-off switching, there is no optical nonlinearity that has been used in here. This is something that, why I'm saying this, because of course I was brought up as a physicist in the 80s, and people say, oh, we know with optical nonlinearities you can overcome the diffraction barrier. And this was kind of misleading, I must say. This kind of diverted the attention of physicists into the wrong direction. Because optical nonlinearities oftentimes are associated with, say, either high intensities or, if not high intensities, at least with some sort of saturation phenomena, but there is no such thing that was used in here. And secondly, keep in mind for this min flux, or for this ideal min flux case, there's no wavelength dependence of the resolution. And this is also kind of mind-boggling. You have now a microscope that works entirely in the far field with just objective lenses. It's all far field, and you get a resolution that does not depend on the wavelength. So if you take red light, it gets the same resolution as blue light. Okay, if the dye, of course, does the transition, that's clear. But other than that, there's no wavelength dependent. That's really showing you how well this diffraction barrier in fluorescence microscopy is really shattered. Thank you very much.
Thank you very much, Professor Hell, for this for sharing with us these stunning results. We have time for questions. So the way I suggest we proceed is please raise your hand if you have questions, and I'll do my best to address them by order, and then you can unmute yourself. And I encourage especially students to ask questions. So yes, please raise your hand if you have a question. Jacob Jungwirth, please unmute yourself.
Hi, I have a question regarding when you talked about the accuracy of the localization, how it depends on the distance between the 2 points you measure and the number of photons you collect. Because from how you presented it, it sounded like that these 2 variables are independent. But to my understanding, these 2 variables are actually very dependent, that the closer you measure to the molecule, the smaller amount of photons you collect from the molecule.
Yeah.
So I just would like to ask if this is some technical issue that you have to overcome by maybe increasing laser power or something.
Exactly. You're absolutely right. What we do is we increase the laser power. Yeah. So we have this additional degree of freedom to increase the laser power, so we can, in essence, have the same number of photons per second. You know,
Okay.
you're perfectly right. And then, of course, you are independent actually as far as the number of emissions concerns from the distance, so to speak. You don't have this dependence anymore, because you have this degree of freedom of raising the laser power. Mm-hmm. And the limit is given actually by the background, because if you crank up, so to speak, the laser power, then of course there's a higher risk of raising background levels. And mm-hmm. so in the practical min flux case, the limit is given by the background. Because if you do that, as you're saying, if you crank up the laser power, then the background is coming up, and then you're not capable of increasing the precision anymore. Yeah. But fortunately, it is such that we can get down to the molecular scale even under normal circumstances. But that's the limitation. And this is also, just to continue on that, this is also why this MinStat concept is very good, because if you increase the power there, you know, then you kind of suppress the background, because the stat beam also suppresses autofluorescence and other fluorescent stuff that is around. But you don't need to change the excitation rate, because the excitation rate is done just by the excitation beam. You can fully control the excitation rate. So that's the conceptual advantage of MinStat over MinFlux.
Thank you.
Any other questions? You can raise your hand by going to reactions. Yes, Oleg, please.
Hi, Stefan. So I'm wondering, for both MinStat and MinFlux, what is the scan pattern when you scan large surfaces?
Yeah, so we have For min-flux, we have used this so far. We have used this, say, 4 points. There is a commercial system that is done by a company that has, there's a spin-off from my lab. They use 6 points. It's also published. It's in this Nature Communication that I mentioned. And for the min-stat, we make a photon by photon decision, meaning that we scan around, and whenever there is a photon, we pull the donut 0 closer to anticipate position of the molecule. So to speak, where we towards the higher emission probability, you know. And so, in my view, the best way to do it is to make a photon by photon decision. But this is not how it was done initially, because if you start out with a project and you don't know how well it works, you're very conservative, and then you want to measure something and then make a decision. But of course, this photon by photon decision is the most effective way.
And for large areas that you showed,
so we scan, so we circle it, and then we have it, and then for large areas we slowly move across the field of view, but
right.
at the same we always circle. So whenever there's a molecule, we start a procedure, and then we locate it, and then we look at whole field of views.
Okay, thank you.
Sure.
Yes, thank you. I would like to ask if this technique is limited to optical wavelength, or you can use it in X-rays, or maybe also gamma rays.
I mean, if you look at localization, then if you think of it as a localization technique, so just finding out where something is, then it applies to any scatterer. Full stop. I mean, you can localize, of course, something better if you have a donut or something like that. You know, that has nothing to do with fluorescence. If you want to do the separation, you need to have a state transition that allows you to separate molecules, and fluorescence is of course great at that, because you can easily, so to speak, disturb fluorescence. You can easily kill fluorescence. You can easily stop fluorescence. And this is why, if you ask me why the diffraction barrier was overcome first with fluorescence, because it's easy to stop it. You know, it's harder to do in X-ray or something. And but if your question is, can I translate this way of localizing molecules to X-rays, or localizing any X-ray scatterer? The answer is yes, sure, for sure, absolutely. If it's about taking images, you have to find a way to separate molecules or emitters.
Yes, but as far as I recall, you started with the optical wavelength, and then you said you cannot do better than 1/10 of this or 1/100 of this. But if you start with shorter wavelength,
yeah, you're better. I mean, of course. I mean, there is still a scaling. Yes, because why is there a scaling in practice? Because there's always background. There's always background. As soon as background comes in, you have a wavelength dependence. Okay, but conceptually, in the min-flux case, conceptually there's no wavelength dependence. But as soon there is background, or a serious background, put it that way, then the wavelength comes into play. Yeah, and then of course a shorter wavelength will be better. Yeah, but again, if the short wavelengths produces a lot of background, there won't be any advantage. But it's still, I think, as a conceptual thought, realizing that there is a way of really getting completely rid of the wavelengths is, at least to me, I mean, for a physicist, at least for me, an optical trained physicist, it's kind of mind-boggling, because you would not anticipate that. But again, in reality, if there's background, the wavelengths dependence comes in, but it's weakened, of course.
thank you.
I don't know if it was clear enough.
Well,
If there is no background, then there is no wavelength dependence, put it that way. If there's background coming in, why? It's very clear, because the background kind of introduces a DC term. And then, of course, the curvature matters. But if there's no DC term, then curvature doesn't matter.
thank you.
Any more questions? Please raise your hands or ask it on the chat. We still have a few more minutes. David, are you trying to ask a question? Yes. Okay. So
I am.
please go ahead.
In the previous question, you were asked about X-rays and gamma rays, but you would need a coherent beam of gamma rays in order to use your approach. Is that correct?
Well, you need of course, you need to have a zero, and then must be some sort of coherence in your beam in order to focus it and produce your destructive interference, because this is how you do the zero. Yes, if it's completely incoherent, then you cannot produce your zero.
In anticipation for waiting for another question, let me ask something that was crossing my mind. What is the mechanical precision of the scanning?
Yeah, that's a good question. It is on the sort of angstrom level. Why? Because the scanning is done electro-optically. So we're using the electro-optical effect. So it's not done with a mechanical scanner. I mean, the core scanning is done with a mechanical scanner. If you scan across a large field of view, it's done with a mechanical scanner, like a mirror that tilts and turns. But this fine scanning that I've shown, that is done electro-optically. And that is, of course, that means no inertia, nothing. You can do it very, very quickly. And this is why we can follow the molecule so quickly and locate things so quickly.
Right. Joel Hirsch asks, has Professor Hell implemented or engineered a two-color system yet? I'm not sure what the question is.
I didn't show it. Yeah, look, I mean, it's a very good question. I have not shown two-color things. Yes, it has been done. So it's published. Yeah, there is a paper in Nature Methods that came out in, I think, January last year that shows two colors. There is, yeah, it's possible. And it's also three colors possible. But I thought that that's maybe not so interesting to this community. Yeah, but it's possible.
All right. If there are no more questions, then let's thank Professor Hell another time for this fascinating talk. And thank you so much for freeing up time to give us your presentation.
Sure, pleasure.
Thank you very much, everyone, and have a good day. Bye-bye.
All the best to Israel.
Bye. Thank you very much.
Bye-bye.
Bye.